Hi folks, welcome to this second lesson on area in the plane. We're looking at two questions here, one where we have multiple points of intersection between curves, and a second one where we have sort of slanted boundaries. To recap our general technique, if we want to find area between two functions, we're looking at the integral from the left to the right boundaries of the top function minus the bottom function. The problem with multiple points of intersection is that if you have multiple points of intersection, the curve that's on top or bottom over different areas may change. So here's the graph of that cubic, and we also want to figure out what's going on with the line g of x. So they both have a y-intercept at 3, and g of x looks something like this. I don't know what the scale is here. I'm just making a rough graph. The thing is, if we want area, so let's put that in purple. If we want this area and also this area, okay, the area that's enclosed by these two functions, well, it's going to have two separate integrals to represent it. One in that first section, where it's the cubic that's on top, and one in the second section, where it's the linear that's on top. We also need the boundaries for each of those sections. At the end of this, I'll show you a GDC hack that can help you get through this a lot quicker, but let's take it as an analytic question to start with. So, points of intersection, we equate the two functions. So we'll have x cubed plus 2x squared minus 2x plus 3, and that's going to be equal to x plus 3. I'll move stuff over. I'll get x cubed plus 2x squared minus 3x, and the 3's will be gone. And I'll factor to try and solve. So the nice thing about this is that x is a common factor. And I'll find out that there are answers, once I factor all the way, of 0, of negative 3, and of positive 1. Those are the x values of intersection. I don't actually care that much about the y values. But back here at negative 3, and I mean, it may look a hair different when we graph it on the GDC. But what we now know is that for that first section, where the cubic's on top, that's going from negative 3 to 0. And for the second section, where the linear's on top, it's from 0 to 1. Now that those boundaries have been inserted, I can start to figure out what this looks like as an expression. On a paper one, there's a good chance, though, that all you're going to do is put in this expression in the first line, and they'll just ask for the expression. So the rest of this is going to be pretty much drudgery until we get to calculator hacks. So there's f of x, okay, minus g of x, which would be x plus 3 dx. I'm actually going to work that out. So that's going to be x cubed plus 2x squared minus 3x, and the 3's will just go. The reason I worked that out is because I now know that if red minus blue is x cubed plus 2x squared minus 3x, then blue minus red is just going to be the negative of that. So here we go. Now you might have other hacks that you want to use. Maybe you want to put subtraction between them and keep the expression the same. But I think this technique is going to work as well. 2x squared plus 3x dx. A lot of places to make silly little mistakes. And then we can anti-differentiate. So that'll give us a quarter x to the 4 plus 2/3 x cubed minus 3 over 2 x squared from negative 3 to 0. And the other one will be the same values, but negativified. So negative a quarter x to the 4 minus 2/3 x cubed plus 3 over 2 x squared. And that is from 0 to 1. I'm going to sub in. One of the nice things is if I put in 0, that whole expression is going to be 0 because there's a polynomial with no constants. And I'm just going to have this stuff appear because, again, it is just drudgery to do this. Okay, I've subbed in. Now I'm going to have to simplify. And again, don't get too caught up in the algebra here or the arithmetic here because this is just painful stuff to get to an answer. And hopefully we'll find a different or better way to get the answer at the end. We have a bunch of fractions. What are we going to need? Common denominator. Let's go. Add them up with the common denominator. We get 71 over 6, or roughly 11.8-ish to 3 sig figs. That was unpleasant working it through, but the big idea there was in the first step. If the roles change, then you need to change the roles in the actual integral. So it's always got to be top minus bottom. And so you'll need a separate integral when those roles change. Now here comes a beautiful GDC hack. If you want the area, you can always go from left to right on the absolute value of one function minus the other. And the left and right are going to be the furthest left and right. We don't care about any points of intersection in between. So in this technique, if you use those absolute values, it doesn't matter which function is on top. And it doesn't matter whether there are other points of intersection. So if we were to use this technique, we could just have said that the area is the integral from -3 to 1 of the absolute value of f of x minus g of x, not caring which one is which. Let's revisit this question with that in mind. So imagine we hadn't done any of the work here. We hadn't found the points of intersection. Let's just go to the GDC with those two functions. There are two functions. Let's hit graph. All I want is the leftmost point of intersection and the rightmost one. So I'll go second, calc, intersect. And let's go to a left bound of around -4-ish. And a right bound. This is slightly different on a real calculator. Tells me there's a point of intersection at -3. And I'll repeat that process, looking for an intersection on the positive side. I don't care about this one in between anymore. There's left bound and right bound, intersection at x equals 1. And that means we're ready to do this whole question very, very quickly. Definite integral from -3 to 1 of the absolute values. That's under math, and hit over for number. It makes absolute value signs. And I can press alpha trace to use y1 minus y2. And because of the absolute value signs, it doesn't matter whether I go y1 minus y2 or y2 minus y1. And there, very quickly, there's the answer. If you want to turn that into a fraction, you can always press math and use the frac button. 71 over 6. So this is actually in your formula booklet, this whole absolute value sort of trick. Though I'm not sure it appears with the two functions. One last question. This one's going to be a GDC question for sure. We want f of x and g of x to have these definitions. L of x is the line tangent to f of x at x equals 4. And this didn't print properly. A is the point of intersection between the line and g of x. So we've got a lot of stuff here. And in the end, what we're looking for is this yellow area. I'm supposed to find the equation of that line, L of x here. So to find the equation of the line, I need a point and I need a slope. So point is going to be, well, it's 4 something. And to find the y value, I just go f at 4, which would be 4 minus 2 squared, or would happen to be 4 again. Okay. The slope at that point, I can find that slope analytically, but I think maybe the slickest thing would be to go to my GDC. I can do it graphically, or I can just go math, and it goes down to n deriv. So I take the derivative with respect to x of y1, which was x minus 2l squared, at x equals 4. And it will tell me the slope there is 4. Again, that wouldn't be hard to find analytically, but now we can do question A. A is looking for the equation, so the equation of a line comes from point-slope formula. So y minus 4 equals m. That was this 4. It's kind of annoying, these are all 4s. Minus, this would be a blue 4 here. So y minus 4 equals 4x minus 16. Or they ask us to put it in this form where it says y equals. Now we have to find the x value of a. Well, now I have this line. Let's head to the GDC. I could try and find the point of intersection analytically here, but I think that's going to be kind of painful. So instead, what I'm going to do is find the point of intersection using the intersect function on my calculator. This emulator has a really hard time when it comes to 3 functions in there, so I'm just going to delete the first one, and I'll graph, and I'm just looking for that point of intersection between this line and that downward-facing parabola. I need to tell it a left bound and a right bound. This will be slightly different on yours. But I'm going to get an x value of 2.83 for the intersection. It's kind of in a brownish color there. So we've figured out that x is 2.83. And now we have to find an expression for the shaded area. And here's the trick. This shaded area can be split up vertically right here. On this first part, it's going to be this little area here is going to be some integral between 2.83 and 4 of f of x is going to be on top and L of x is going to be on bottom. On the other hand, this section right here is going to be the integral between 2, because this is at 2 here, and 2.83 of f of x minus g of x. And if you added those two things up, you'd get the full yellow area. So let's write that down. The area is going to be the integral from 2 to 2.83 of f of x is on top, and g of x is on bottom. You could use some absolute values here if you weren't sure about top and bottom. Plus, in the other section, it's bounded on top still by f of x, and on bottom by that line. And you could put in all the gory details of the x's and y's there, or all the x's and the squareds, but it's pretty nice just with the f's, g's, and l's. The last question is to actually find this, so clearly that's going to involve our GDC. I'm going to put my y1 back in. That's f of x. So y1 is f of x, y2 is g of x, and y3 is L of x. And now I can just go math, fn int. So it's between 2 and 2.83 of y1 minus y2. That first little region, it's just looking at the area between the two parabolas, plus another integral between 2.83 and 4 of the top parabola, which was y1, minus the tangent line, which we've now put in as y3. My emulator had a little bit of a hard time with it, so I had to go and do it in pieces, but in the end I get 0.915. That's probably about as rough as these questions are going to get for us, where we have these slanted boundaries. When you have a slanted boundary, though, try and split it up into 2 parts, split up with a vertical line. For practice, you can check out page 459, numbers 1 to 5, and you can do any of the chapter review on page 461 to 463. I hope this has been helpful. Good luck with the material, and take care, folks.